Okay.
Hello, sir.
Good evening.
Good evening.
Today we will talk about those topics. Eigenspace, Cayley Hamilton, equations. This is Cayley. And another thing will be diagonalization.
What is the second one? K.
Cayley,
Caution.
Cayley Hamilton equations.
Okay.
You have asked me a question that previous day you have asked me to if it is true or not. That is, if something is isometry,
Yeah.
then A is real matrix. Then is it imply A is orthogonal?
Yes. Yeah, this was an assignment question, sir.
Okay. Have you figured out this thing?
Yes. Actually, I asked on the discussion. So, what they told is that it is both ways. Like, if
Yes.
it is an
So
isometry,
previous
then
day we have seen this part. So let us try the reverse side, opposite side. So suppose norm x equal to norm x for all x. Suppose this is holding. So we can write this x comma x comma y. Suppose this is the inner product. X and y are any vector from V. That is V is Rn here. Sorry, V is actually this is Ax. V is Rn. That is X and Y belongs to Rn. A is n by n matrix. We are assuming those things. Then let us see what is the inner product.
sir, can we see the question once again?
That is the question is if something is isometry x equal to x, this is called isometry. Then that is non-preserving. The linear transformation or the matrix multiplication is non-preserving. Then we need to prove that A is orthogonal.
Yeah, sir. Okay. So can I read the question once again? Like here it is saying, consider a linear transformation T from R3 to R3
Yes.
defined by Tx is equal to Ax.
Yes.
Then A is orthogonal if and only if T is an isometry.
Yes. T is isometry means actually Tx equal to x. But here Tx is actually Ax. That is multiplication by the matrix A. This is why I am directly considering this.
Okay. So the right side, you're saying A into A transpose is equal to identity.
Yes. We need to prove this part. A into A transpose is identity. Or this part also. You can take this part, whatever.
Yeah.
So you can write this thing using that polarization equality. That is polarization identity, or directly you can see that this is actually x ay square minus norm of ax minus ay square. Okay, and you need to take 1/4 of this. This is the same type of equality which holds for real number. It is a plus b whole square minus a minus b whole square. This is 4ab.
Yeah.
That is exactly that part. And now if we use the isometry part, then you can see that norm of ax plus ay. This is actually a times x plus y. So using isometry, you can write this as 1/4 of norm x plus y whole square minus norm x minus y whole square, right? Because of this fact, instead of x, we are now considering x plus y and x minus y. Okay. So now again the same parallel, whatever this equality called, this is same as norm x comma y, inner product of x comma y. Okay.
Sir, Ax is equal to x. Can you please help understand, like, why are we assuming Ax is equal to x?
By the hypothesis is norm of norm of a x. This is same as norm x. This is true for all x belongs to Rn, right? So instead of x, we are now taking x plus y, and this will give norm x plus y. Okay.
No, sorry, sir. Actually, I didn't get this. I understood. Like, you are just taking x in place of x. You are taking x plus y. But the initial assumption that Ax is equal to x,
Yes.
that is not a part of the question.
That is given because the thing is that here it is given that it is isometry. T is isometry, and isometry means this. Actually, isometry means non-preserving. If you apply the transformation, then the norm after the transformation is same as previous.
Okay, okay. So lambda is one, something like that, right?
Lambda is one, we can say, but
Okay.
eigenvalue will be unit vector. That is
Got it. Yeah, got it.
okay. So now you can, it is now just manipulation. That is now you can write a star ax, or instead of star, transpose, because it is a real number. A transpose ax y, this is same as x comma y. Now in particular, uh, this will imply A transpose Ax equal to x, right? Why this is true? Because take in particular, take y to be A transpose Ax. If you put that, this will imply A transpose Ax. No, this is actually not working.
Sir, I am also trying to.
This is not working, but uh, this will imply A transpose Ax equal to x. Why this is true actually? Why? Because, sorry, because let us see. This is actually A transpose Ax minus x times y equal to 0 by distributive property. And particularly take y to be this thing, A transpose Ax minus x. Okay. Then we'll get A transpose x minus x times A transpose x minus x. This inner product is 0. Right?
Sir, how did we get the A transpose Ax minus x? And then we still have y.
Because this will imply this minus this equal to 0, right?
Yeah,
And
but
now
y minus
this is
y.
distributive property.
Hmm.
Distributive property of inner product. That is, if inner product satisfies linearity in each component.
Yeah, but then y also will become 0, right? Y minus.
Then no. X and y are independent vectors. So we can particularly take y to be this, right? X and y, we have chosen x and y any vector from Rn. And
Hmm.
now in particular we are putting y equal to this. And this will give this inner product is 0. Up to this, is it okay?
No, sir, I'm not very clear about the step above this.
Which
Like,
step? This step.
yeah, yeah.
Okay. You know this fact, right? U v comma w, inner product of this. This is same as u comma w plus v
Hmm.
comma w. That is distributive property of inner product.
Yes, yes, yeah.
That is what we are using. Instead of plus, there is minus actually. Here it is minus. Then it will be minus.
So we have this and this. Okay. Uh, okay. Yeah. Got it.
Because inner product satisfies the linearity property. That is, if you multiply something, then take inner product. This is same as first inner product, then multiply with that scalar.
Mm.
That is why minus is also allowed, or any scalar is also allowed.
Okay.
So this is actually norm of A transpose AX minus X, norm square. By definition, this is actually norm square. And you know that norm is always non-negative thing. So norm of something is 0 means this is actually A transpose AX minus X, this is actually 0. And this implies A transpose AX is same as X. This is again for all X belongs to R. Okay. In particular, if you take X of this type, X of this form 1, 0 and everywhere 0, then this will imply A transpose A. Now, if you multiply with X, that is multiply with 1, 0, 0, this is actually same as 1, 0 and 0 everywhere. Okay. Similarly, if you multiply, take another X, choose X to be this form. Okay, E2. Then we will get A transpose A times X. X is now 0, 1. This is actually 0, 1 and 0 everywhere. So
Mhm.
if we take X in this way, then you can see that A transpose A times 1, 0 and 0 everywhere, 0, 1, 0, that is 0, 0, 1 and 0. And the last entry is 0, 0, 0 and 1. This is actually same as, that is we are taking all the columns now.
Mhm.
Instead of this single column, we are taking all the columns together. That is, you can thought multiplication in this block form. And this is actually same as 0, 0, 1, 0 and then 0, 0, 1. That is, we are taking the same thing. So now you can see that left hand side, this is actually identity. So A transpose A, and the right hand side is also identity. This is actually identity. So now,
Mhm.
therefore, A is orthogonal.
Okay. Mhm. Okay, sir. Thank you.
So,
Sir, one more question was there in the last week's quiz.
what is that question?
Just a second, I'll. Um, if every skew symmetric matrix is diagonalizable over R,
Yes.
so they have.
Okay, I have seen that question you have asked already, but
Uh,
actually, this that answer is wrong because over complex it will be diagonalizable, but over
mm,
real it may not be diagonalizable. It is
yeah, because even we did this in the practice last time also in the class when you took the tutorial.
yes, yes,
That time we exactly proved that it is not for the skew Hermitian matrix.
yes, because eigen values can be complex number also. So
Correct.
over real number, it may not
So
be.
in exam, shall I mark it as true or false? How they will mark grade it, I don't know. Uh,
I also don't know, but you may ask. They will help you regarding this.
and the first question also, so in the first question in the assignment 7, it
Okay, what was that question?
uh, state whether true or false.
Hmm.
Square real matrix A
Hmm.
uh, is diagonalizable over R
Is diagonalizable over R?
if and only if A is equal to EUF.
Yes, yes. I have given the answer. in your it is just now. Then actually P inverse AP, this is actually a diagonal matrix. Okay.
Yeah.
But instead of this, if you take, suppose P is, now you can see that P is invertible. So you can choose P to P is same as Q inverse, right? You can take this.
P is equal to Q inverse. Yeah.
Because P is invertible matrix.
Mm-hmm.
So this will give this fact Q inverse is same as D.
Yeah.
So those are equivalent definition. Diagonalizability of A you can define in this way also or this way also. It does
So,
not.
sir, the question is something else here.
Okay, what
EUF.
was that question?
EUF is, they are saying that U is an upper triangular matrix.
Mm, okay, instead of D, it is U, upper triangular matrix.
Yeah.
Okay.
So they are saying A is equal to EUF, where E and F are invertible, and U is a upper triangular. And they are asking whether it is true or false.
What is A equal to UEF?
EUF.
Okay.
E A is equal to EUF. U is upper triangular,
Okay.
and E and F are invertible.
Okay.
So they are saying, is this true or false? And A is diagonalize square matrix diagonalizable over R. So
Okay. Can I put it in this form?
they are saying that if A is a diagonalizable matrix, then if and only if when this condition is met, is this true or false? That's what they are asking.
Mm, okay.
I gave it as true because, like, I just guess. I didn't do any derivation. I
Uh,
just
okay.
that
You you may ask in that chat. I will try to solve and reply. It is not, the question is not clear to me now. So
sir, I can share my screen for quickly so that you can see.
instead of doing this, you should ask in the chat. Then it will be, because
Okay,
we
fine.
need to start the topic, new topic.
Sure. Yeah.
Okay, thanks.
Thank you.
So we have already familiar with eigenvalue and eigenvector. What is the meaning of eigenvalue? Eigenvalue is some lambda belongs to the field F. Here the field is always a real number or complex number. Okay. So a, suppose lambda belongs to F and given A is a matrix. So if there exists some non-zero x such that Ax equal to lambda x, okay, there exists x which is non-zero vector from this Rn n cross 1 matrix. Then lambda is said to be an eigenvalue of A, and the corresponding vector x is the corresponding eigenvector. Eigenvector. Now we can see an interesting fact that suppose lambda 1 and lambda 2 are two distinct real number or complex number, whatever. Then, and also consider v1 and v2 are corresponding, are eigen values corresponding to lambda 1 and lambda 2 respectively. Then the claim is v1 and v2 are linearly independent. Okay. then V1, V2 are linearly independent. Li. How do we prove this? It is easy to prove. So suppose A is the matrix or A is the transformation. So given V1 is the eigenvalue corresponding to lambda 1. So we can write A V1, this is same as lambda 1 V1. And another thing is given that A V2 is same as lambda 2 V2 because V2 is eigenvalue, eigenvector of A corresponding to lambda 2. Those information are already given. So we need to prove V1 and V2 are Li. So what do we assume? We assume this thing. Let C1 V1 plus C2 V2, this linear combination is 0. Then this apply A, that is multiply with A. Okay. Left multiply with A. And this will give C1 times AV1 plus C2 times AV2 is 0 by distributive property. And this will imply, now we use those properties. Okay, this will imply C1 lambda 1 V1 plus C2 lambda 2 V2. This is 0. Now consider this equation and this equation. If you use this operation, so 2, if you multiply lambda 1 with this and subtract, that is 2 minus lambda 1 into this one and subtract, then we'll get C2 lambda 2 V2 minus C2 lambda 1 V2. This is 0. That is, if you take common, then it will be lambda 2 minus lambda 1 times C2 V2. This is 0. Now you know that V2 is non-zero, right? V2 is non-zero because V2 is eigenvector. Eigenvector cannot be 0. So this will imply now, and another thing is lambda 1 and lambda 2 are distinct. Okay. So this thing is also non-zero and this V2 is also non-zero. This will force C2 to be 0. And similarly, instead of this, if we do the opposite thing, we'll get C1 equal to 0. Okay. Those two things imply that V1 and V2 are linearly independent. Now instead of those V1, V2, if we this result generalized to n linearly, that is, suppose lambda I are distinct eigenvalues and Vi's are corresponding eigenvector. Then, okay, eigenvalues are and eigenvector of some matrix A, it is given. Then the claim is that those Vi's are linearly independent. I equal to 1 to n, those lambdas here I equal to 1 to n are linearly independent. The proof is the same thing, that is, we'll assume this combination summation Ci Pi is 0, I equal to 1 to n, and successively we apply A, that is, first apply A, that is A times, this will automatically imply A times sum of Ci Pi, this is 0, and this is distributive property will imply Ci times Avi, this is 0. Now lambda is the corresponding eigenvalue, then this is implies Ci times lambda Vi, lambda I Pi, this is actually 0. Okay, so we are getting, initially this equation we are considering Ci Vi equal to 0. Okay, now applying 1a, we are getting new equation, that is Ci lambda I Pi. this is 0. Instead of lambda I, let us write in this way, lambda I times CIPI. This is 0. Now again, if we apply A again, then we will get this equation, lambda I square CIPI, this is 0. And similarly, up to, if we apply n minus 1 times, we will get this thing, lambda I to the power n minus 1 CIPI, this is 0. Now you can see this is actually a equation with van der Monde coefficient. Okay. So if we put all those equations together, it will be of this form. That is, first will be 1 1 1 everywhere. Then it is lambda 1, lambda 2 up to lambda n, and nth row will be lambda 1 to the power n minus 1, lambda 2 to the power n minus 1 up to lambda n to the power n minus 1. And though this is not a correct way because C1 P1 are vector, but we can put those things. Cn Pn, this is 0. Now you can see, if you consider this as some coefficient b, then you can check determinant of b, determinant of this types of matrices will be of this form, lambda I minus lambda j, where I is strictly greater than j. We have already seen that fact. And since lambda and lambda j are distinct, this is given, those are distinct eigenvalues, and this is actually non-zero thing. Okay, so since determinant is non-zero, then this will automatically imply C1 V1 up to Cn Vn. This solution will be trivial. Okay, note those 0 are not 0 from the field, those are 0 vector. Okay, because we are considering equation with vectors. C1 V1 are not arbitrary thing, those are actually vectors. So this 0 actually consisting these 0 vectors. Okay, so we have written this thing. Since determinant is non-zero, we are getting unique solution. That is 0 is the unique solution. This we now again we know V1 up to Vn are non-zero because of the fact that those are eigenvectors. Okay, eigenvectors cannot be 0. So this will imply C1 equal to 0, C2 equal to 0, up to Cn equal to 0. That is another way, other word, V1 up to Vn, those are linearly independent. So this is the conclusion. Up to this, is it okay?
Sir, can I ask?
Yes.
So linearly independent, when we are proving, like earlier when we used to prove, then we used to say if these vectors are linearly independent, then their scalar combination would be uh, like we we cannot derive any vector in the set from each other, right? So none of them is a linear combination of each other.
Yes, yes.
So,
This is what do you mean by linearly independent?
so sir, that time we used to make a determinant and we used to prove that it has this row reduced echelon form we used to make, and then we used to show that it is rank full rank, right?
Yes.
Now here we are having a multiplication of scalar to the vector.
Yes, we have. I have already said that this is not a right way of writing, but this is, if you solve this system, this is equal to 0, and if you apply the row reduction, you will get actually this equation precisely. Okay, instead of vector, we are assuming this vector has some variables.
Yeah.
Okay, that
So,
is what is the difference.
my question is how from this we are concluding, like what is the
So this is, if you consider this is actually b times x equal to 0. Now b is invertible. B is invertible means x equal to 0, right?
Okay.
Multiply with B inverse. That is what we are getting.
So we are okay. Okay. Got it. Yeah.
And now we are comparing each rows. C1 V1 equal to 0. But V1 cannot be 0. V1 is a non-zero vector. This will force C1 to be 0.
Yeah, that is fine, sir. So if C1, C2 is 0, then how do we conclude that V1 are linearly independent?
Because
V1,
this is the definition. That is, any linear combination is 0. This will implies all Ci are 0.
Okay, okay.
This is the definition of linearly independentness. And
Okay.
we
Yeah, if any combination, then only the coefficients can be 0 for linear.
yes, only trivial.
Got
Yes, Ravi is right. Only trivial solutions. Now we'll consider another thing. Uh, Let us state this fact. I'll not prove this. Cayley Hamilton equation. Hamilton theorem actually. What does this theorem say? So we have seen that given a matrix A be an n cross n matrix, then there exists a characteristic polynomial. What is that polynomial? Determinant of A minus x equal to 0. This is the characteristic polynomial. And the Cayley Hamilton theorem, this says every matrix n by n matrix satisfies its own characteristic polynomial. Polynomial. Characteristic equation, sorry. This is actually equation, not polynomial. So this is the theorem. Instead of explaining this, let us see an example, then it will be easy to understand. So, consider identity matrix. So what is the characteristic equation? Characteristic equation will be like this: determinant of 1 minus x, 1 minus x. This is 0, 0 equal to 0. And this is same as 1 minus x whole square equal to 0. Okay. And this is same as x square minus 2x plus 1 equal to 0. If you see this, that if you put I in this equation, this is actually not allowed because x are from the scalar field. Okay, here those x are from scalar field. But this theorem says we can put the matrix itself. Okay, so if you put I in this equation, then we will get I square minus 2i plus 1 is now identity matrix. Now you can see that this is actually 0. Okay, so this theorem is stating this fact, that given a characteristic equation, we can put characteristic equation into that, we can put the matrix A into the characteristic equation and it will be satisfied. So now this is actually 0 vector, 0 matrix, n by n matrix, 0 everywhere. 2 by 2 matrix in this case. This is actually 0. This is the Cayley Hamilton theorem. Let us see another example. So consider A is same as 1, 1, 1, 1. Now what will be the characteristic polynomial? Determinant A minus xi equal to 0. Characteristic equation. So this will imply 1 minus x, 1 minus x, 1, 1. This determinant is 0. And this is, now if you factor, this will be same as x times x minus 2. This is 0. Okay. Now if you put A into this equation, let us consider this equation star. Put the value of A in the star. Then it will give A times A minus 2. Not 2, it will be 2y because 2 is nothing in matrix, so we need to take 2y. Now you can see that this is actually, let us calculate explicitly. A is 1 1 1 1, and what is A minus 2y? This is, we need to subtract 2 from the diagonal. It is 1 minus 2 and 1 minus 2 and 1 1. That is, this is actually minus 1 minus 1. This multiplication will give 0 matrix. So this is what Cayley Hamilton says, that if you put A into the characteristic equation, it will be satisfied. Okay, this is a non-trivial thing, that it is not clear directly why this is proved, but Cayley Hamilton proved that fact. That it will be true. Let us talk about diagonalization. So consider this matrix A to be this. Then we want to diagonalize this. That is, we need to find a P from some GL2R, that is non-invertible matrix. Non-invertible matrices are called GLNR, general linear group. So we need to find P such that P inverse AP, this is diagonal matrix. We need to find P and this D such that this satisfied. Okay. Then this is called diagonalization of A. Given a matrix A, and we are diagonalizing A and we are getting D. This process is called diagonalization. Okay. So let us see this. Instead of doing this, let us see an important technique. So suppose A be an n cross n matrix, and there are some eigenvectors lambda 1 up to lambda j, lambda 1 up to lambda n. This can be repeated eigenvector also. And corresponding to lambda 1, we are getting an eigenvector v1. And lambda n, we are getting another eigenvector vn. Okay. Then, and we are assuming that v1 up to vn, those are linearly independent. Okay. So lambda 1, lambda I may not be distinct. They can be repeated. It may not be distinct, but we are assuming v1, the corresponding eigenvectors are linearly independent. Okay, we are assuming this fact. Then we want to claim that then A must be diagonalizable. How do we prove that? Let us do diagonalization of A. Okay, so we are given A v1 is same as lambda 1 v1, and A v2, this is same as lambda 2 v2, up to A vn, this is same as lambda n vn. Now put those equations together in the matrix. So we'll get A v1, A v2 up to A vn, putting those in columns. Okay, those are n by 1 matrices. We are putting those matrices together. So we are getting now n by n matrix. So this is actually same as lambda 1 v1, lambda 2 v2 up to lambda n vn. Now the interesting fact is that this is same as A times these matrices V1, V2 up to Vn. And the right hand side, this is actually V1 up to Vn and multiply it with this diagonal matrix lambda 1, lambda 2 up to lambda n. Okay, this is the interesting observation. Sorry, this is same as V1, V2 up to Vn and then multiply with this diagonal matrix lambda 1, lambda 2 up to lambda n, 0 everywhere. Okay, if you multiply this, it is easy to see that if you multiply this with this diagonal matrix, you will get this right hand side. Okay, because lambda 1 times this will give the first column. Lambda 2 times this will give the second column. Just usual matrix multiplication. We are doing nothing but matrix multiplication. So now let us give name this. Let this equal to P. Okay, so this thing is same as P. Assume that. So this implies A times P. This is same as P times this diagonal matrix. Let us give name. This is assume this as D, a diagonal matrix. So AP is same as PD, and let multiply P inverse. Then we will get P inverse AP equal to D. So this is the proof. Okay. So if for n by n matrix, if there are n linearly independent eigenvectors, okay, those are linearly independent eigenvectors. Then the claim is that A is diagonalizable, and the converse is same. The converse is true by the same way. Okay, given P inverse AP equal to diagonal matrix, then those diagonal entries will form eigenvalues, and this column of P, this will form the eigenvectors. So converse is also true. It is not then this is if and only if. Let us see this example, then it will be much easier to see. Consider this example. How do we diagonalize? Instead of this example, let us consider a big example, then it will be general case. So let question diagonalize this matrix A, which is 1 0 0 0 0 and 1 2 1 2. Okay, so what is the characteristic equation? Characteristic equation, it is given by determinant of A minus xi equal to 0, and this is same as 1 minus x 2 1 2 minus x equal to 0. And if you solve this, you will get the equation will be like this 1 minus x. If you multiply this, and another thing will be x, and this is 3 minus x equal to 0. Okay, so you can see how can I write it directly, because the fact is that trace I am using that fact. Trace is same as sum of eigenvalues. Sum of lambda is the same as trace of the matrix. So here you can see that one will be a eigenvalue, one will be an eigenvalue because of this. You can take 1 minus x common, and so now we need to consider this block. You can see this block actually non-singular.
Sir,
Singular.
trace. Sir, please एक बार trace definition can you please tell?
Trace means sum of the diagonal entries.
Okay.
So
Sum of the diagonal entries is equal to trace of A.
yes. So I am saying that consider this block. We let us consider only this block. Okay. So for this block, this is actually this thing. Here we are finding eigenvalue of this matrix actually 1 to 1. So for this matrix, you can see this is actually singular matrix. Determinant is 0. So determinant is 0 means 0 is an eigenvalue. Okay. So there will be another eigenvalue. What will be that eigenvalue? You can use this fact. Okay. So trace is 3 minus 0. So one eigenvalue is 0, another eigenvalue is 3. That is why I am getting this equation. So this is the characteristic. Yes, thank you. So this is the characteristic equation, and therefore we are getting the eigenvalues 0, 1, and 3. Those are the eigenvalues. So let us find vector corresponding to those eigenvalues. Corresponding eigenvector. So for x equal to 0, what do we get? A times x equal to 0 times. So this is v equal to 0 times b.
Sir, I'm sorry to stop you once again.
Yes.
सर पिछला वाला मुझे बहुत क्लियरली हुआ. Can you please derive and show?
Okay, I am saying that this is actually this is actually, we know this fact together with another fact, that is product of lambda I. This is determinant of A, right? So since this is 0, determinant of this actually 0. So you can say that one eigenvalue will be 0.
Product of lambda I is equal to determinant of A.
Yes. So since determinant is 0 here, so there is 0 will be eigenvalue, right?
Okay.
Because otherwise product can never be 0 if there is non-zero, all eigenvalues are non-zero.
Sir, yeah, just quickly, because so determinant of A is the full matrix, right? Why we are taking submatrix of it?
Okay, so you can see this is actually same as 1 minus x times this submatrix, right? 1 minus x to 1 2 minus x.
Yeah.
That is why I am not considering the first part. I am considering only the
Okay.
second part.
So, sorry, I'm not still able to see. Okay, so if we take 1 minus x out, that means that is definitely an eigenvalue 1.
Yes. Now
But
we need to find the other eigenvalues.
yes.
So you can see one eigenvalue will be 0. If you consider this block, that is eigenvalue of this matrix, one eigenvalue is 0 because determinant is 0, and another eigenvalue will be 3 because trace should be 3.
So trace of A is 2 plus 1 plus 1, 4, right?
No, I am considering this block.
Okay.
Even if you consider this A matrix, then you can see that one eigenvalue is already 1, another is 0.
Okay,
So
so
you subtract 1 and 0 from this trace.
more than 3 is left. Okay.
Okay.
Yeah.
Oh.
Yeah. Thank you.
Okay. So let us see what are the eigenvectors. So eigenvectors corresponding to 0, we will get AV is same as 0V by definition of eigenvector. V belongs to this n by 1 matrices. V must be non-zero, and this will imply. So let us V in this form: x1, x2, x3. This matrix. So this will give 0 0 0 sorry 1 0 0 0 1 2 0 1 2 times x1 x2 x3 is 0. So how do we solve? We'll just row reduce. So first row will be 1 0 0 0 1 2, third row will be cancelled 0 0 0. So what are the solution of these matrices? So a solution, non-zero solution, 0 is already a solution. A non-zero solution of this equation will be, so you can see that third column does not contain any pivot. That is why you can choose third column independently. So last entry can be chosen anything. So I am choosing 1. Then the second equation says x2 plus 2x3. This is 0. Okay. x2 plus 2x3 is 0. So since x3 is 1, so x2 must be minus 2. Solving this. And the first equation says x1 equal to 0. So this will be 0. So this is a solution. Okay. And let us, sorry. Need another page. Sorry for this. So we have figured out one eigenvalue, one eigenvector. So this is an eigenvector corresponding to this eigenvalue x equal to 0. Now consider x equal to 1, this eigenvalue. Then the equation is a minus lambda I. Lambda means 1. So a minus I times v is 0. So we need to subtract 1 from the diagonal. Okay. Then we will get this thing is same as 0 0 0 0 0 2 0 1 1. This times x1 x2 x3 is 0. This is actually row reduced. So again we just need to exchange rows, that is 0 1 1 0 0 2 and 0 0 0, row reduction. So from here you can see that the solution, again a non-zero solution of this equation is the same as, now first column does not contain any pivot. That is why we can choose first entry to be anything. So I am choosing 1. Then this will automatically imply x2 plus x3 is same as 0, and another thing is x3 equal to 0. So since x3 is 0, it is 0, and x2 plus x3 is 0, then this will also imply x2 equal to 0. So we are getting this non-zero solution for this corresponding to x equal to 3. So x equal to 3 means we need to consider this equation, a minus 3i times v equal to 0. So this is actually same as, okay, 1 minus 3, that is minus 2 0 0 0 0 here, 1 2, that is 1 minus 3 minus 2 2, and 1 2, that is minus 1. This times x1 x2 x3 is 0. Okay. So now again this is actually, if you do row reduction, this is 1 0 0 0 1 1, and other entries are, third row will be 0. So you can see that third column does not contain pivot. We can choose, so again a solution, non-zero solution will be this. So third entry can be chosen anything. We are choosing 1. So this will imply x1 first row gives x1 equal to 0. The second row gives x2 plus x3 equal to 0. Now since x3 equal to 1, therefore x2 will be minus 1. Okay, and the first equation gives x1 equal to 0. So this is the non-zero solution. So what is the diagonalization? We are getting 3 equations, right? 0 minus 2 1. So we are getting a times 0 minus 2 1. This is same as, what is the lambda? First eigenvalue was 0. So 0 times this. 0 minus 2 1 times this 0. Okay, this diagonal entry is 0 now. Now we'll put the second column. Second column is this, the second eigenvector corresponding to 1. So it is 1 0 0 corresponding to 1. Okay, 1 0 0. So we are getting this thing. Another eigenvector is 0 minus 1 1, 0 minus 1 1 corresponding to the eigenvector x equal to 3. So we'll put 0 0 3 in the corner. So this is the diagonalization. That is, this is the diagonal matrix D. This is P. We are getting AP equal to PD, and this will imply P inverse AP equal to D, where P is given by this. P equal to this matrix. Okay, this is the process of diagonalization. You have already noted that fact, right? That singular, a matrix is singular if and only if there exists a zero eigenvalue.
Yes, sir. So you already told that product of lambda is equal to determinant of A.
By this.
So then one of the lambda.
0, then one of the lambda must be 0.
Yes.
This is the fact.
Yeah.
Right. So let us now solve some problem. Those are actually problems from GATE. I have taken those problems. Those are interesting. Let us solve those problems. So here the first question is, M is 5 by 5 matrices and all entries are 1. Then the question is M diagonalizable or not? This is the main question. So here M is this matrix 1 1 1 everywhere, 5 by 5 matrix. Five by 5 matrices. Then the question is, M is diagonalizable or not? What is the answer? So this is an important question actually. You can see that rank of M is 1, right? Because all rows are completely determined by first row. All rows are equal to first row. If you row reduce, it will become 1 1 1 in the first row and everywhere 0. Okay, that is why it is rank 1 matrices. So if rank of M is 1, then what will be the rank of the solution space? What will be the nullity? So rank of solution space, this is 5 minus 1, right? Because we need to subtract rank from this by rank nullity theorem or by just matrix equation, theory of matrix equations. So rank of the solution space, that is nullity, is 4. Then this will imply corresponding to the eigenvalue 0, there exist 4 linearly independent eigenvector. Right? Because what this implies? This implies here we are saying that rank of the solution space is 4. That is, there are 4 linearly independent vector v1, v2, non-zero linearly independent vector, such that those are 0, right? And 0 means actually 0 times v1, 0 times v2, and similarly 0 times v4. This implies v1 up to v4 are eigenvector corresponding to 0. Is it okay? So, yes.
Not very clear.
So, I am saying that corresponding to 0, we are getting 4 linearly independent eigenvector.
Okay. Yeah, because the
Because the
rank,
solution space will give those eigenvectors.
because only first row is non-zero.
Yes.
So each one will be a free variable
Yes.
and only one non-free. So we will have that many independent linearly.
Independent solutions.
Okay.
So now we have yes, earlier we have seen the theorem which says if there are 5 linearly independent eigenvector, then we are done. Then A must be diagonalizable, right? So
Yes.
now what will be another eigenvalue? 0 will be eigenvalue whose multiplicity is 4. That is, 0 is appearing 4 times here. Okay. Now what will be another eigenvalue? So we know that sum of eigenvalue, this is same as trace of the matrix M. For this case, trace is actually 5. Okay. So all the eigenvalues are 0. There are 4 0 eigenvalues. So 0, 0, 0, 0. So that non-zero eigenvalue, this must be 5, right? Now the eigenvector corresponding to 5, this must be linearly independent from the rest. Li, this must be linearly independent because we have already proved that fact. That is, corresponding to two distinct eigenvalue, the eigenvectors are linearly independent. We have already proved this fact. So we now this will imply that there are actually 5 different eigenvectors, 5 linearly independent eigenvector. First 4 linearly independent eigenvector together with the another eigenvector corresponding to lambda equal to 5. So since there are 5 linearly independent eigenvectors, therefore M must be diagonalizable. So the first answer is correct. Now the second says M is idempotent. Is it true? Earlier day we have seen that idempotent matrices. Idempotent means A square equal to A. So idempotent matrices has eigenvalues either 0 or 1. Because lambda satisfies also this condition, lambda square equal to lambda, therefore we are getting lambda equal to 0 or lambda equal to 1. So you can see here that there exists a eigenvalue lambda equal to 5 which is not same as 0, not same as 1. So M cannot be idempotent. Can M be nilpotent matrix?
Sir, can you please explain by writing? Not very clear.
Okay. So if we consider the second, it will be clear. So suppose M nilpotent.
No, the second one only, sir.
Which thing?
Idempotent.
Okay. Suppose M is idempotent. Idempotent means M square is same as M. Now apply X. Apply the eigenvector V. Suppose lambda is an eigenvalue, and V is the corresponding eigenvector. Okay, then we are getting mv is same as lambda v. We'll get this. Now multiply this thing with v. It will give, this side is actually lambda square v, and the right hand side is lambda v. This implies lambda square minus lambda times v equal to 0, but v is non-zero thing because v is eigenvector. This will imply lambda square minus lambda equal to 0. Therefore, lambda is 0 or 1. Okay.
Okay. Sir, so in this, the question was, is it idempotent, right?
Yes. So from here you can see that it cannot be idempotent.
So, so since we have lambda values,
Because idempotent matrices, eigenvalues of idempotent matrices must be 0 or 1. But here you can see that 5 is also eigenvalue for this matrix. So it cannot be possible. Right?
oh, so you're saying that this 0 and 1 is the eigenvalue of m
Possible eigenvalues.
if and only if it is lambda is 0 or 1. But since we have more than 0 and 1
Yes, we are
values,
having
it
more than 0 and 1, and that will imply m cannot be idempotent.
okay.
Similarly, for nilpotent matrices, we know that nilpotent matrices has eigenvalues 0 only. The possible eigenvalues are 0 by the same way. Okay, so m cannot be nilpotent. Now the last question says minimal polynomial and characteristic polynomial of m are equal. So what will be the characteristic polynomial? Characteristic polynomial, this is same as this thing, that is determinant of xi minus a, and since we already know what are the solutions, so since 0 and 1 are the only solutions, so it will be x, and x, and another solution is 5, sorry, not 1, it is 5 is the eigenvalue. So this is characteristic polynomial is actually this. Okay. Now, what is the minimal polynomial? Minimal polynomial is the polynomial that is, we know that every matrix satisfies its own characteristic polynomial, but there can be a smaller polynomial which can be satisfied that by that matrix. Okay, the smallest degree polynomial is said to be minimal polynomial. If it is not clear, let us consider this matrix. So suppose A equal to 0. Okay, so this matrix satisfies those equations, x equal to 0. So characteristic polynomial for this A, suppose A is 2 by 2 matrix, then characteristic equation will be x square equal to 0. Okay, that is characteristic polynomial is x square. But you can see that A equal to 0 already satisfies these equations, x equal to 0. Okay, so the smallest degree polynomial which satisfied by the matrix will said to be minimal polynomial.
So sir, you are saying that if we remove all the common factors, then the smallest order of
Yes.
x that will become the minimal polynomial. Okay.
Not no, we are not removing every degree, but we are removing until A satisfies these equations.
Yeah. So in this case, say for example, x raised to 4 into x minus 5,
Yes.
we can remove x raised to 4 to x only. So we have x into x minus 5.
Yes.
Okay.
So that is, you can check that x into x minus 5, this is actually satisfied by m. That is, m times m minus 5i. This is actually 0. You can easily check this fact. Because diagonal entries, this is m and m minus 5i. This is will be of this form, right? It will be minus 4 in the diagonals and 1 other things. And if you multiply this, it will be actually 0. You can easily see that multiply this with this thing, this will give you 0, and multiply everything, it will always give you 0.
Hmm.
So that is why minimal polynomial is actually x squared, that is this thing, x times x minus 5, and this is not same as the characteristic polynomial.
Hmm. Sir, so in exam, say supposing they ask us to find minimal polynomial, and
Yes.
we go just by step because I am
Yeah,
new to the
yeah. Step by step, in this way you can do. Uh,
just
First,
find.
you should start with x minus 5. If it
Hmm.
is 0, then you will stop.
Okay.
Now, if it is not non-zero, then you need to square the second. Okay. Now, if it is 0, then you will stop. And now, if it's non-zeros, then you will again continue.
Okay.
That is how we find minimal polynomial.
Sir, and one more that C part, but can you please tell once again the C? I'm
See,
sorry, I
okay,
missed.
it is okay. Uh, M is M cannot be nilpotent. Why? Because nilpotent matrices have determined has eigenvalues 1 eigenvalues 0. Because suppose M is nilpotent, then M to the power k equal to 0. Okay. Now again, if you uh, use the same trick, M to the power k into V equal to 0, V is eigenvector corresponding to lambda. Then this will imply lambda to the power k V. This is 0. This will give lambda to the power k equal to 0. This will give lambda equal to 0. That is, all eigenvalues will be 0. For nilpotent matrices, all eigenvalues are 0.
So here also one of the eigenvalue is 0, right?
But there is another thing, lambda equal to 5, which is non-zero.
Okay. So
Eigenvalue must come from only this, lambda equal to 0.
okay.
Because we are taking any eigenvalue, lambda, and we are claiming that, we are proving that lambda must be 0.
Okay, sir. Thank you.
5 cannot be. Okay. So let us see this question. Here, the question is if M is diagonalizable or not. So when will it be diagonalizable? You can see that eigenvalues eigenvalues are actually 1, 2, and 1 by because of the diagonal end. We know that upper triangular or lower triangular matrices eigenvalue will be diagonal entries. Now, so for 2 we'll get a linearly independent eigenvector, but for 1 it will create problem, because corresponding to 1 there are two possibilities. That is, one possibility is eigenvectors, there are only single one linearly independent eigenvector, or there can be two linearly independent eigenvector. Okay, there are two possibilities, so we need to figure out when those occurs. So corresponding to 1, we need to consider this equation, m minus 1 times I into v is
So
same as.
here we are assuming that since it's a diagonal vector, a diagonal matrix, so 1, 2, and 1 are the eigenvalues, right?
No, it is upper triangular matrix. Therefore,
Hmm.
1 to 1. Because how do you find this? You need to subtract x from those entries. And
Correct.
now, what will be the determinant?
Yes, sir, I got that. So we are starting with assuming, with the understanding that 1 to 1 are the eigenvalues for.
Yes, those are
Okay.
the eigenvalues.
Yeah, thank you.
So 2 is not problematic because 2 will give a linearly independent eigenvalue, eigenvector, but 1 is problematic because multiplicity of 1, it is actually not equal to 1. It is multiplicity is 2. So
Algebraic multiplicity.
yes, algebraic multiplicity is 2. We need to figure out if geometric multiplicity is 2 or 1. Which cases will occur? So we need to figure out that thing. So m minus I, this is actually same as 0, 1 and 0 here. It is A, B, C. Now you can see that when does this equation, this times V equal to 0, when does this equation has single solutions? One linearly independent solution and two linearly independent solution. So the question is, when the there will be two linearly, we need to figure out the condition for which two linearly independent solution exist. Because diagonalizable, if and only there are three linearly independent eigenvectors. Okay, one linearly independent eigenvector is already present corresponding to 2, but we need to find other two linearly independent eigenvector corresponding to 1. Okay, so two linearly independent exist. When will it exist? If and only if rank of this matrix, suppose this is B, if and only if rank of B is 1, but rank of B is 1, this is if and only if this should be 0, right? If this is non-zero, then we'll get rank is 2. Okay, that is why this must be 0, and this is 0 if and only if AC minus B is 0. So this is the answer. AC equal to B. So this is the answer. Is it okay up to this?
Sir, if we go by simple steps, like I understand you have used a lot of understanding of this matrix and
Yes.
derived this. Say if we go by simple steps as a beginner,
Okay.
then
So let me repeat those again. So I am saying that corresponding to 2, we are already getting one linearly independent eigenvector. So this is diagonal if and only if there are other two linearly independent eigenvector. Okay. So
yeah,
other eigenvector will appear because of these eigenvalues.
yes,
1.
yes,
Now corresponding to this 1, we are trying to figure out the eigenvectors.
hmm,
And eigenvectors are can be understandable by this equation.
yes. This I understand, sir.
Okay.
Only little bit the final part where we concluded things
Yes.
like that
So
part.
we need to find the condition when this equation has two linearly independent solutions.
Hmm.
So when this will hold, there are two linearly independent solutions. When will it be true?
So rank of B is equal to 1 means that uh,
Because nullity is 2, and we know that nullity is 2 if and only if rank is same as the n by n matrices n minus nullity, right?
hmm,
Nullity is 2 here and n is 3 here, so
hmm,
rank must be 1.
okay.
And rank must be 1. This will automatically imply this should be, the determinant of this should be 0. That
Hmm,
is, the second thing is some linear, some multiplication of the first
hmm,
one. That is why I am writing this, and this will automatically give AC minus B equal to 0.
hmm. Okay, fine.
Okay. Is it visible? So how we concluded nullity is 2, because we are not concluding this. We are assuming, we are trying to figure out the condition for which nullity will be 2, because we need three linearly independent eigenvector. One is already present because of this. Okay, so other linearly eigenvector must be appear because of corresponding one, and we are trying to figure out the condition for which there will be two linearly independent eigenvectors.
Sir, here if we just solve the equation, the matrix which we have in the middle, uh,
Yes.
by that we can just say that x3 is equal to 0, right?
Yes, x3 is 0.
And x2 plus x3 is equal to 0, which x2 plus cx3 is equal
x2
to 0,
plus cx3 equal to 0, right?
which means again x2 is again 0. And so, sir, how did we get to
Yes, you are right. Then this will give ax1 plus ax2 plus
bx3?
bx3 equal to 0.
Yeah, and x2, x3 is already 0. Then how we are getting two vectors?
Uh, no, how do you get x3 is 0? This is not true, right? Here you can choose x1 to be, because x3 is not free. The first column does not contain pivot, though, so first entry can be free. So
Okay.
you can choose first entry to be 1.
Mhm.
Yes, yes.
So if we choose x, first entry can be 1 because
Yes,
first column is 0. So then x3 can be uh, its corresponding value. Okay.
yes. So by this way, it is difficult to figure out the condition. In this way, you can easily find.
Mhm.
So for this question, it is given that T satisfies this property. There are 16 V1 up to V16. There are 16 vectors which satisfies this property. TV1 is same as V2. TV2 is same as V3. Up to TV15, this is same as V16. Okay, and another property is this. For last vector, this will satisfy this. V1 up to V16. So what will be the matrix representation for this linear transformation? The matrix representation will be like this. So if we consider this, this will give the second entry is 1, 0, 1, 0, and everything is 0.
Sir, can you please go a bit little slow? I'm just still reading the question.
So the question is, those are order basis from complex number C16. Okay, this is the vector space C16, and given T is linear transformation on V defined by this formula. Okay, I have written explicitly in this way, and the last formula is this.
Okay.
Then there are some options. So what will be the matrix representation? It will be like this, right? And the second column will be 0, 0. This is V3. So third position will contain 1, coefficient 1, and everything except this is 0. Similarly, 0, 0, 0, 1, 0. And it will continue up to this. Here it will be 1. And now the 16th column will be, coefficients are 1 for every entry. It will be 1, 1, 1. Everything is 1. Okay. Now you know, that is, how do you find determinant of this thing, determinant of a minus xi? We need to find this, right, for characteristic equation. So you know that determinant of these types of matrices we have already familiar with this type of matrices, that is, those are called companion matrices. So companion matrices will look like 0, 1. That is, diagonal entries are 0, and the last entry can be anything, a0, a1 up to an minus 1, and below the diagonal it will contain 1. Okay, this is how component matrices look like. And we know that for those types of matrices, determinant of a minus xi, this is actually same as a minus xi. Let us consider this determinant xi minus a. This is actually same as the characteristic polynomial. Okay, that is, it will be like this: a0 plus a1x up to n minus 1 x to the power n minus 1 plus x to the power n. This was done in the determinant class. Let us see an example. Consider these things: 0, 1 and 0. A0, A1. For this, if you subtract minus x, that is x minus this, or subtract in this way, minus x, then it will be minus a1x minus a0. Okay, that is why we are getting in this form. In general, this actually generalizes this fact. So if you are not familiar with this, you should again try that exercise. I have already given in the determinant class. That is, for companion matrices, determinant will look like in this way.
Sir, where it is given? Sorry, I didn't get it.
In the determinant lecture 4, we have considered this type of matrices. These matrices. Below the diagonal, those are 1, and the last column will be a0 up to n minus 1.
Okay.
Okay. For those type of matrices, the polynomial, characteristic polynomial will look like this. Now let us come back to the equation. From this fact, it is clear that the characteristic polynomial, if you consider the coefficient, now coefficients are 1, right? So it will be 1 plus x square up to x to the power 16. Okay, this is the characteristic polynomial. So now can you see this? What will be the solutions of this equation? You can see that this is actually 17th root of unity, because x to the power 17 minus 1, this is same as x minus 1 times x to the power 16 plus 1, this thing actually. So 17th root of unity, but x cannot be 1. So solutions are 17th roots of unity, and which is not equal to 1, because we are not taking 1 here. X minus 1 is already factored out. That is why all other roots of 17th root of unity. So from this, you can see that 0 cannot be solution of this equation, because 0 will not satisfy this polynomial, right? 0 will not satisfy this equation, determinant of a minus xi equal to 0. Because those are 17 roots of unity. So t is singular, it is not possible, because 0 is not an eigenvalue. So t is regular. This is the answer. But now, what are the eigenvalues? Eigenvalues, are those rational or other non-rational numbers? So, since 17 is prime, so all the other roots will be complex number, because if you divide this circle into 17 portions, then all the other roots must be complex number. Okay, that is why this is the answer. No real number can satisfy this equation. This equal to 0. This cannot be possible by any real number. This must contain some imaginary part, because 17 is prime. If you divide the circle into 17 portion, then only this is the real agenda. This is the real solution. X equal to 1, but which is already factored out. Okay, factor out from this equation. X to the power 17 minus 1 equal to 0. So all other roots are completely imaginary. That is, this must contain some complex number. That is what I am saying. Is it clear?
Sir, x raised to 17 minus 1.
Yes.
We factored out x minus 1 from it,
Yes.
and then the remaining equation is a uh, even powered
Oh,
equation. So
I think there will be 15. Sorry for this. No, there will be 16, right?
yeah, no, I'm just also thinking in some other way, saying that since it is even, so there won't be any real roots of that.
Okay, you can use those Descartes rule or those types of rules. You can use that.
Okay, and so what you're saying is that since there are no real roots, uh, so there is no uh, like
Yes. There are
rational.
no real roots, so there cannot be any rational eigenvalues. This is what I am claiming.
Okay.
Let us move to the next problem. It is actually difficult, because difficult means not that much difficult, but I am. Let us solve it partially. So
Sir, it is very difficult. I request you if you can go a little slow because for you it is easy,
okay,
but
okay. Sorry for
for
that. Sorry for that.
no, it's okay. But I just want to say, like for us, it is little difficult. At least for me, it is difficult. I
Okay,
don't.
yes.
Yeah,
I should. So up to this, is it clear?
yeah. So somewhat like this one, not fully, but yeah, I got roughly. I got what you are saying here. Yes.
Okay, okay.
Yeah.
This is actually the main problem is to figure out what are the solution of this. Zero cannot be a solution. So zero is not an eigenvalue. Therefore, it is non-singular. Non-singular here they have said it regular. That is invertible.
Okay. Mm-hmm.
So we need to figure out the other thing. The
Mm-hmm.
eigenvalues are rational or not. So this can be seen from this fact, that is, this is actually all the other 17th root of unity except one, and all the other roots, those are actually appear from this equation, x to the power 17 equal to 1. That is the whole circle, this divided into 17th equal portion. And this cannot lie on the real number, because there are only two possible real solutions, plus 1 and minus 1. You can see that minus 1 does not satisfy this equation,
Mm-hmm. Yeah.
because right there are 17 terms. Okay, minus 1 plus 1, this will appear alternatively, this will cancelled out, but 1 will remain.
Mhm.
That is why no real solution can be possible.
From this equation. Yeah.
Yes, I think now it is clear.
Yes.
Okay. So for this question, let us not consider this part. It will be time consuming. So here we already know 3 is the eigenvalue by the same technique we have just given in the previous example. So we need to we need to figure out eigenvalue of 6226 this block. So the question is that we need to figure out the eigenvalue of these matrices, this matrix A equal to that matrix, and we need to figure out the what are the eigenvalues. If you subtract x from the diagonal, then it is clear that 3 will be an eigenvalue because it is similar to the previous exercise. Okay, so one eigenvalue will be 3. So this cannot be answered because this does not contain 3. This cannot be answered. So we need to figure out what are the other eigenvalues. So let us consider only the second block, 6226. So from this block, you can see that determinant of this block, this is actually 36 minus 4, 32, and trace is same as 6 plus 6, that is 12. So except 3, let us remove 3 from everything. Then product of those things must be 32 and sum of those things must be 12. So for 7 5 the product is 35. So this cannot be an answer. This is already not an answer. Yes, 8 4 satisfies those properties. Product is 32 and sum is 12. So this will be the answer. If this is clear, let us the next. Swati, is it okay?
Yeah. So, sir, can I just say once what how you solved it?
Yes.
So, sir, because it is diagonal, a kind of a diagonal
Block
matrix.
diagonal. Yes.
Yeah. So that's why we started with just taking. We know that trace of the we know that trace of the matrix is equal to the sum of the
Eigenvalues.
yes eigenvalues. So 6 plus 6 12 should
12.
be the sum. We removed one of them, which is 3, because 3
3.
is already there, lambda.
Yes.
Uh, so rest of them saw the combination. The sum is 12,
Yes.
and so product should be 36, 32.
32.
6 is 36, right, sir?
Because determinant is 36 minus 4.
Oh, minus 4, yeah, determinant. Okay.
Yes.
Okay, so determinant should be equal to just a second.
Determinant should be equal to product of the eigenvalues.
Okay, so sir, earlier we had a formula product of the diagonal elements is equal to determinant of A. Okay.
For
Yeah.
the upper triangular matrices.
Okay, okay. Got it. Yeah. So that is a quick way of solving this.
Yes. Quick way of solving those kind of problem is if it is block diagonal, then consider the problem separately for those entries. For 3, consider this is a separate equation. For this block, consider another separate equation. That is how.
Thank you.
Okay. So let us consider another problem. Yes. So this is an interesting problem. There are two questions. One question is this, another question is. So consider question 1. Here A is given in this way. A is actually this matrix 1 0 0. Oh, this is actually not that. Sorry, 1 0 0 I omega 0 0 0 omega square. Omega is the third root of unity, complex root of unity. Okay. So from here we can say that eigenvalues are those, right? Eigenvalues are the diagonal entries. So eigenvalues, because it is upper triangular, lower triangular matrices. So eigenvalues will be 1, omega, and omega square, right?
Yeah.
Now this is eigenvalues of A. Eigenvalues of A. So what will be the eigenvalues for A to the power 102?
A to the power 102. Okay.
We have seen this fact, right? If Ax equal to lambda x, then it will imply A to the power nx is same as lambda to the power nx. Inductively, we have seen this fact.
Mm-hmm.
That is, this implies that if lambda is an eigenvalue of A, then lambda to the power n is an eigenvalue of A to the power n.
Mm.
So for A to the power 102, the eigenvalues will be 1 to the power 102, omega to the power 102, omega square to the power 102. Okay. So those will be the eigenvalues. Yes.
Now,
Yes.
how you found this? I didn't get it.
How do you? How are we getting this identity? This thing.
Yeah, this one we are saying ax is equal to lambda x, and then
Successively apply A again. Multiply with A.
okay,
X
so,
equal to lambda x. Then A x. This is same as A lambda x.
yes. So we got like again we got ax, then again it became lambda x. So that way
Lambda
we are
times lambda x. That is lambda square x.
okay. So a n x it became equal to lambda n x.
Yes.
But how the root became like this? Can like the root of a raised to n minus lambda raised to n I. Uh, how we found this so quickly, like 1 raised to.
Because we have seen this trick, right? Ax equal to lambda x.
Mhm,
Then apply A again. Multiply with A. This will give A square x equal to A times lambda x. But this
mhm,
is same as lambda times ax. And this
mhm.
is again lambda square x. And
Yeah.
multiply successively.
So
This
we
will
got
give A cube x equal to lambda cube x.
yes.
Similarly, we are getting this thing.
So this I understood. Yeah. But this root 1 raised to 102 and omega raised to 102, how
Yes.
we this
Okay.
one?
How do we get this?
Yeah.
Actually, 102. 102 is same as if you divide it by 3. That is 3 times 3, 9, 0, right?
Mm,
So this is actually same as omega cube to the power 34.
mm.
But omega cube is same as 1. So this is actually 1. And similarly, this is also 1.
Okay, this one. Okay.
So for a to the power 102, all the eigenvalues will be 1, 1, 1. Those eigenvalues will be 1, 1, 1. So sum of the eigenvalues is 3. Therefore, trace will be 3. So D will be the answer. Is it okay?
A little fast this is. So I'm still
Okay,
thinking.
let us repeat again. A to
Yeah.
the power 102, the eigenvalues are those, right?
No, so this part is not very clear. How we concluded this?
Because if A has eigenvalue lambda, then A to the power n has eigenvalue lambda to the power n because of this fact.
Okay, but we have to take the root characteristic polynomial and then
We don't
find.
need to take those things. We are
Okay.
using the definition actually. X equal to lambda x. Since lambda is an eigenvalue, there exists some non-zero x such that Ax equal to lambda x.
Okay.
Okay, x is the eigenvector.
Hmm.
And successively applying A again and again, we are getting this equation.
Hmm.
This will imply this. And this is the actually definition of eigenvalue. Okay, there exists some non-zero x for which A minus some mu times I into x equal to 0, then mu will be eigenvalue.
So from here, we are concluding that since we already know the roots of A,
Yes.
uh, which is so because of A raised to n is equal to lambda raised to n, we
Yes.
are thinking that for this also, it will be raised to n. The roots will be raised to n, right?
Yes.
Okay. So once the roots, we find the roots, and then you are saying that the trace of A raised to 102, uh,
Equal to sum of the eigenvalues.
yes, sum of the eigenvalues, which is 1 raised to 102 plus omega raised to 102 plus omega square raised to 102. Now, but as per you, this omega cube is equal to 1.
Yes.
How we have concluded omega cube is equal to
Actually,
1?
actually, I have remembered this part. This is actually cube root of unity. Okay.
Okay, okay,
This is actually cube root of unity. Complex.
okay,
So we know one thing will be omega, then other will be omega square.
okay. I think, yeah, this is the part I was missing completely. Okay,
Okay.
fine.
Okay.
Okay. So that's why it is D. Okay.
Can you solve the second question?
Which of the following is not
Not diagonalizable. So what about the part B? Is it diagonalizable?
determinant is not 0. Uh,
We need to check there are two linearly independent eigenvalues. We need to find two linearly independent eigenvalues.
and it is a diagonal matrix. Sorry, it is a lower triangular
Got
matrix.
triangular?
So lambdas are 1 and 2.
Yes.
So it has two eigenvalues.
Two
One,
eigenvalues.
hmm. And vectors, how will we find? We have to solve the equation, right?
Now I have I have proved a fact that if eigenvalues are distinct, then the
Mhm.
corresponding eigenvector must be Li,
Must be
linearly independent.
linearly independent. Okay. Mhm.
So there
Yeah.
are two
So
linearly
this is
independent.
this is diagonalizable then.
Okay,
Yeah.
so this is diagonalizable, so this cannot be the answer.
Mhm.
So consider the next case. Uh,
Uh,
can it be diagonalizable?
this one is a skew symmetric matrix, and skew symmetric matrix has uh,
Don't consider this. Let just consider what is the trace of this thing.
trace is 0.
Zero and
So
determinant
trace is 0, so, and determinant is uh, 1.
minus one. Sorry, one.
1, yeah.
So are those eigenvalues same or different?
Trace is 0 and
Trace
determinant
is
is
zero.
1.
Suppose eigenvalues are same, then two lambda should be zero and lambda square should be one. Is it possible?
No, it's not possible, sir.
It is not possible. So this will imply those eigenvalue cannot be same. Lambda 1 and lambda 2 must be different. Otherwise, their sum will be 0 and their product will be 1, which is inconsistent. So
Yeah.
this is again diagonalizable. So,
Okay, because lambdas are different, so it
yes.
is okay. Hmm. Yeah.
Now, what about the last option, D?
This is a upper triangular matrix, and then uh, again like lambdas are same.
Lambda
So
the same.
yeah, lambdas are 1 1, and
So let us try to figure out what is the eigenvector. So we need to subtract 1 from the diagonal, right? Since 1 are the eigenvalues are 1.
yeah, so it will become 0
0, 1, 0,
0 0, and x y. So
x1, x2, 0. Consider this equation.
both are 0. I think so. X1,
You
x
can directly see, right? The rank of this matrix is 2, 1. Rank is 1. So solution space, what will be the rank of the nullity? Sorry, rank of the solution space. What will be the nullity? Nullity is this 2 minus 1, that is 1.
mm-hmm,
So solution will only contain one Li vector, one
mm-hmm.
linearly independent. So
Okay.
this is not diagonalizable. So this is an answer. So what about the first option?
First one, 2 minus 1 1. Determinant is 1, and sum is 3.
Yes, sum is 3. So let us try
So,
again to see what are the possible eigenvalues. If
mhm.
those eigenvalues are same, then their sum will be 3 and their product will be 2 minus 1, that is 1. So is it possible?
Lambda square is equal to 1. That is lambda is equal to plus minus 1. No, it's not possible.
Not necessarily, because lambda can be complex also. But
Okay.
if you use this fact, lambda is 3 by 2,
Mhm.
then lambda square can never be 1.
Yes. Mm.
That is why this is also not true, because this is diagonalizable.
Mm-hmm. Okay.
So great. Let us think about the next question. So again, this is similar to the previous. So we need to find the trace of this matrix. Okay. I plus m square.
Find the trace of the matrix.
What are the eigenvalues of m? Yes, eigenvalues are the diagonal entry 1 alpha, alpha square, alpha cube, alpha 4. Those are the eigenvalues, those 5 entries. So, what will be eigenvalues of m square? It will be square of this, not same, the order will be different. So, it will 1 alpha square, alpha to the power 4, alpha to the power 6. Alpha to the power 6 is, since alpha is fifth root of unity, alpha to the power 5 equal to 1, right? So alpha to the power 6 is same as alpha, and this is alpha to the power 4 to the power 2, alpha 8, which is same as alpha cube.
Sir, can you please go a bit slow? This is not very clear. What's going on?
I am just querying those eigenvalues. This will give eigenvalues of m square.
Sir, so here the first, this alpha is equal to e raised to, that exponent is not very clear. What is
It is
written?
actually e to the power 2 pi I by 5.
Okay.
That is fifth root of unity, complex root.
Okay. And the matrix is this. And then they are saying find the trace of the 1 plus m square.
Yes, I plus m square.
Mhm.
Now there are two ways. One is directly square those things and add. But instead of doing this, we can do in this way also. Okay. I am claiming that eigenvalues will look like this. Eigenvalue of I, identity matrices have eigenvalues are all I, all are one, right? For for identity matrix, all eigenvalues are one. For M, the eigenvalues are this from this given matrix. And for M square, the eigenvalues will be square of this. Okay.
Sir, m square without multiplying, how you're
Because
concluding?
of the previous fact, we are using the same fact. Mx is same as lambda x. This will imply m square x is same as lambda square x.
Hmm.
That is why this says that m square has eigenvalue lambda square. Corresponding to the same eigenvector, we are getting the eigenvalue lambda square.
Mhm. Okay.
So, so from here, what will be eigenvector of eigenvalues of I plus m square? We need to take the sum of those things. That is sum of these three, then again this 1 alpha square. We need to sum in this way. But sum in rows ways, column ways, is same as sum of rows. But if you consider this row, if you consider this row, the sum is 0, right? Because alpha to the power 5 is 1. So alpha to the power 5 is 1. This means alpha minus 1 times alpha to the power 4 plus alpha cube plus alpha square plus alpha plus 1. This is actually 0. Since alpha is complex, so this thing is, yes, absolutely. Sum of the roots equal to 0. Since we are talking about roots of unity.
So, sir, then second row is 0.
Yes, second row is 0. The sum of third row, it is again 0 by the same fact. And sum of the first row will be 5. So sum of everything, this is actually 5, right?
Hmm. Okay.
And we are trying to do that, trying to figure out what is the sum of those eigenvalues. So first eigenvalue is 3, second eigenvalue will be 1 plus alpha square, third eigenvalue will be like this 1 alpha square alpha to the power 4, and we are adding those all those eigenvalues.
Everything will be 0 except the 1.
Yes, except the first row, and this will give 5.
Yeah. Okay.
That is why trace will be 5. Actually, those questions are tricky.
Sir, 1 will be taken from all the rows, right? 1, 1, 1.
Yes. Uh, if you do in this way, those three, then you need to pair all those entries because there will be 15 entries. You need to cancel those in other entries. That is why instead of doing in the row way, in the column way, we are doing the sum in this with rows.
Okay. 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 So, sir, the third row will become 0 because you are taking out the alpha raised to 5 and reducing it to again the same equation alpha 5
Yes,
plus alpha 3.
sum of those entries.
Okay. So, third row also becomes 0.
Yes, it is right. Let us solve the last question. There are many questions remaining. So, here, M is Hermitian or skew Hermitian? What will be the answer?
Skew Hermitian. Or
Skew
just
or Hermitian? Normal. Hermitian means this definition. Conjugate transpose is same as M.
it's a Hermitian.
Hermitian, because you can see those are same except conjugation.
Yeah.
So if you flip around the diagonal, only you need to do conjugation. Okay, so that's why it is actually Hermitian. So if M is Hermitian, then automatically IM will be skew Hermitian. So this is true. Okay, because M star equal to M, then IM star. By definition, this is actually M star times I bar. And this is minus IM star, so, which is same as this. So if M is Hermitian, IM will be automatically skew Hermitian. So
So
M star
in
equal to M, we are using this fact.
so in skew we have this imaginary part is negative, right?
Yes.
Here, except for -4, that real entry, the complex part is skew only. This is conjugate only. Uh, only thing is,
What are you saying?
sir, sir, you are asking, right, ki whether this is Hermitian or skew Hermitian.
Yes.
So I'm just trying to confirm this once again.
Okay.
Because here, if the complex ones are, so skew Hermitian is uh, the conjugate transpose, right?
Yes.
And so
No,
conjugate
skew Hermitian means this equation. M star is same as minus M.
M. So this is like conjugate transpose is equal to minus M.
Yes, conjugate transpose is same as minus M.
Okay. And so this one here, in this case, uh, if we take a transpose, it will be 2, and then conjugate will have is uh, it will happen if we take a transpose, right? But
Yes,
minus will not come.
minus will come because of the conjugation, right?
Uh, so like this minus M will not happen, right? Minus
So
M.
let us see this. What is M star? So the first row will be now 2, 3 plus 2y and
Mhm.
minus 4. But we need to take conjugation of this.
Yes. Hmm.
So conjugate, if you conjugate, then you will get 3 minus 2y.
Yes.
So
So this isn't this then skew Hermitian?
then it is Hermitian, right? Because M star is same as M. We are getting the first column will be 2, 3 minus
Okay.
2y and
Uh,
minus, and which
so
is already given.
okay, so for it to be skew Hermitian, even
Yes.
the real
For Q Hermitian, we need to uh, take the sign. We need to change the sign. That is, first entry will be minus 2. It will be minus 2, minus 3 plus 2y, and minus
Mhm.
plus 4.
So this is a symmetric matrix then in a way, like is this analogous to
Yes, it is analogous to the symmetric. That is, Hermitian is actually symmetric. You can see that this is actually symmetric, and there is another part. Okay, so real part is actually symmetric. 2,
okay.
3, minus 4.
So if in a complex world, if we want to make a if we want to make a symmetric complex matrix, then we have to take a conjugate
We need to take
for complex matrix.
For complex matrix, symmetry actually means this Hermitian. That is, we need to take conjugation and transpose also. Otherwise, those properties, that is A transpose A,
Yeah.
that is inner product property, those properties will not be satisfied.
Okay. Okay.
That is
Okay.
why we are modifying the definition of transpose.
Okay. So M star has to happen even for symmetric also.
Yeah. For symmetric, if it is for symmetric, the definition will be same. That is, for symmetric, it will M transpose is same as N.
Yeah. And if it is complex, M star has to be equal, M transpose equal to M star. Uh,
No, no. For complex also, there are two different things. One is symmetric and skew symmetric.
yeah.
But this is completely different from Hermitian and skew Hermitian. Okay.
Hermitian, I thought Hermitian was the concept we used.
Hermitian is analogous to symmetric, but it
Yeah.
is not a symmetric thing.
Sir, can you please explain this? This is not.
Because you have seen those properties, right? Because for example, if you do inner product, we
Mm.
for real entries we don't need to care, that is we just multiply x into x. But
Mhm.
for complex, x plus iy times x plus iy, if you multiply in this way, that is multiply x plus iy with x plus y iy, this will give this thing.
Yeah, it will be, there will be one minus coming.
Yes.
Mm.
So that is why we need to modify the second thing. We need to take x minus iy.
Okay.
This is the motivation behind this Hermitian or skew Hermitian.
So
Because
sir, then if for a, say supposing in exam it is given a complex matrix like this, and then they say write the uh,
yes,
Hermitian matrix for this,
yes,
then I have to take conjugate, right?
yes. Write the complex conjugate. Then you need to take transpose and then conjugation.
Transpose also. Okay, okay. Mm-hmm.
Is it okay?
Yes, yes,
That
yes.
is what I was doing in this.
And if it is a skew, then only to the complex conjugate.
Then you need to do another thing, that is negative. You need to include.
Okay. Sir, can you please write the skew Hermitian for this? How we can write? Like,
Okay, skew Hermitian will be skew Hermitian. That is, we need to see that m star if it
so,
is same as minus m.
okay. So, sir, can I tell like what will be the skew for this matrix M?
Okay.
It is it like 2 and then mine
So diagonal entries
will
cannot
become
be
0.
real, right?
Yes, yes, yes. Triangle will become 0. And,
No, not zero. It can be purely imaginary.
oh,
Because if you do purely, suppose this entry is I, okay, 2i. Then uh, if you just apply star, m star, that is you are taking bar of this entry, right? This is minus 2i,
mhm.
and this is actually same as minus m.
Okay.
Because
Well,
this is actually not m. This is
hmm.
actually I was considering I
Sir,
times
if you
I.
can take a small matrix 2 by 2 and just explain quickly, that
Okay,
will be
okay.
fine.
Yes,
Yeah,
yes. This will be nice. So
it's not very clear.
consider this thing. Okay. So it is okay, all right. So 1, 2, 3, 4. 1, 2, 2, 1. This is symmetric as well as it is Hermitian.
Mhm.
Okay.
Mm.
Why Hermitian? Because here conjugation has no role.
Mm.
Now let us consider this part. Now, can you add something here? Can you add that? Can you add some imaginary thing in the diagonal?
Uh,
Will it remain Hermitian? Let us try. What is A star? By definition, it is 1 plus I, 2 with conjugation, 2, 1 with conjugation. 1 minus y, 2, 2, 1.
so
A star
transpose.
is not same as A.
Sorry, since we are doing 8 star, isn't it transpose, including transpose?
Yes, transpose and conjugation. We are doing two things.
Mm-hmm.
One is we are transposing and we are taking conjugation of each entries.
Sir, so on the right hand side of the A star equation, do we want to write transpose on the top?
Which thing? We have
The
already taken transpose, right?
no,
1
but
plus
we
I,
are,
2. This is same as 1 plus I, 2 1.
mhm. Yeah. Okay, okay.
But you can see that this is not same as A because of this imaginary part.
Hmm.
So for in general, you can prove easily that for Hermitian matrix, diagonal entry must be real, purely real.
Okay. Mm-hmm.
Okay, because conjugation should be same as the same term.
Mm-hmm.
That is so. Now, what will be eigenvector of M? We already know that what are the eigenvector of Hermitian matrix? Those are completely real, right? Purely real.
Yeah.
And
Mm-hmm.
what will be eigenvector of Im? Skew Hermitian matrix?
Complex.
Purely imaginary.
Yeah. Purely
So
imaginary. Yes. Mhm. No
just
real.
the previous class.
Mm.
That is why the only answer is U and R. This is the
Eigenvalues M are real.
yes. Is it okay?
Sir, I'm still thinking, but you can proceed because otherwise, lot you have a lot of
I will
questions.
stop here actually. It is
Okay. Oh, it's beyond the time. Okay. Uh, Sir, so then can you please clarify my questions also? I'm
yes,
not
yes. What is
clear.
your question?
So this Q and R, is M is Hermitian and IM is Q Hermitian.
Yes.
If I multiply by I, then
Yes.
it become two. So how did you solve this part like without even like putting pen and solving? I how I will approach is like I will multiply by I and then I'll check. Uh,
For this question, how do we check if this is Hermitian or not?
no, like IM is Q Hermitian.
Okay, Im is Q Hermitian because you can use this fact, right? You know this thing A A times B transpose. This is same as B transpose times A
Transpose
transpose.
A transpose. Yeah.
And this is true for star also. For conjugation and conjugate transpose.
Okay.
Okay.
Hmm.
Now what is I times A? I times x star. What is this? You can write a times identity I star, and this is same as identity I star times a times a star. This is same as minus identity I times a star. This is same as minus I times a star.
Mhm.
If it is not clear, you can just take a paper and pen. Then you can directly check by the definition.
Mm.
Okay. You should start with an easier example. For example, 2 by 2 matrix or those type of things.
Yeah.
For example, if you should try with this block, 2 by 2 block, then it
Mm.
will be much easier. Then you should generalize the result, what is happening in general, and you'll get this fact. You should take an arbitrary thing, a plus ib, c plus id. Okay, then try to prove this fact.
Okay, sir.
Is there any other doubt?
No, sir.
Okay, Ravi, is there anything?
Sir, is this the last?
Yes, this is the last, our last meeting. Okay. Can you tell some reference book for problems? Okay, here I was using that. There is a book, AP Singh's Gate question paper. I was using that book for this last lecture. Those are those appears from this book.
AP Singh.
Yes, yes, it was. I have used this book, AP Singh, for my gate preparation. You should look at this book. There are those questions are already there. Yes, yes, previous year questions.
What is PY? Previous year question, sir.
Yes.
Mhm.
For NBHM, you should look at this book, uh, Mittal. This was another nice book which will be helpful for your net gate, net or jam. Sorry, net or NBHM.
Okay, sir. Thank you.
Okay. Thank you, everyone. It is
Thank
very
you.
nice journey. Thank
Yeah,
you.
thank you. Very good class, sir. Really good.
Welcome. Let us stop here.